Today we are going to talk about the limit theories, and then we will continue. Well, after that we will talk about a random process. For the limit theory, first let's see what is sum of random variables. So suppose I have x1 to xn, and they are a sequence of n random variables. If I sum all these random variables together, it is still a random variable. It's called sum of random variables. I can also divide by n since I sum n random variables, and this is the mean. And since x1 to xn, if I plus together, it is still random variable, so the mean is also random variable. So based on this definition, Sn is the sum of n random variables, and m is the mean of these n random variables. Here is a note. So x1 to xn are random variables. Therefore, Sn and m, those are also random variables. And since they are random variables, then we will be interested in the distribution. What distribution of S and M are. And then for this M, we call it the sample mean. The sample mean is an empirical average of a sequence of random variables. Empirical means that if I have 5 random variables, then I just find the mean of these 5 random variables. If I have 100, then I just find the mean of these 100 random variables. So this sample mean may be different from the true mean. And for this true mean, let's see. The sample mean is a random variable. So here, the sample mean is a random variable. But the true mean, this true mean is a fixed number, deterministic quantity. And in practical, we don't have the true mean. We can only estimate the true mean through our sample mean. For example, the average age in Taiwan, this is the true mean. And then it's pretty hard. Actually, it's almost impossible to find this true mean. But we can do the survey for the average of 10,000 people in Taiwan. This is the sample mean. And as long as I can find enough people or random variable, then this sample mean will be approximately equal to the true mean. Let's see the sum of the random variables, the expectation, and also variance. So for the expectation, if I want to find the expectation of the sum of n random variables, so for the linearity, so I can find the mean or expectation for each random variable and sum them together. And for the variance, also the variance for the n random variables, sum of the n random variables, I will find the variance of each and sum them together. And then I need to consider the covariance. Each covariance x1 and x2, x1 and x3, till x1 and xn, until the covariance xn to xn shouldn't be xn to xn. It should be this one will be the variance. So it should be xn minus 1. And if you switch this order, it's the same. Let's see an example. N is a random variable. So Sn here, n is a random variable. So Sn is the sum of n random variables. Then I want to find the expectation of this sum of random variables. And also we assume that for each mean, the mean of each random variable is mu. So how do I find the expectation of Sn? Be careful that now for this one, this n is now random variable. Okay, in the beginning, we know we have n random variable, but in this example, this capital N is random variable. So it depends. This n may change. It'll be 5, 10, 100, or 10,000. So it's different. So how do I find the expectation? So for this expectation, since we don't know the n, we need to fix n first. So to fix n, we will do the condition. When n equals a fixed number, so n could be 0, 1, 2, 3, 4, 5 till infinity, right? Then I need to consider O. And then we need to times the Pn. When n, the capital N is fixed, this expectation is just the summation I from 1 to lowercase n x I in Pn. So this is the sum, and then what is the expectation? We assume that their expectation is O mu. So there will be mu plus mu plus mu plus mu for n times. So I have n mu and then Pn. So I can put mu outside and do the summation. N times the PMF of n. So here I consider all possible outcomes times their weightings. This is the expectation. Therefore, we get mu times the expectation of n. For limit theories, today we are going to learn actually two and a half limit theory. The first one is called the weak law of large number. So what is weak law of large number? And why do we need to learn this? Because we know that we have true mean and sample mean. Normally we cannot get the true mean. We have to rely on the sample mean to approximate the true mean. But how close or how good the sample mean is. So here, how good is the sample mean compared to the true mean? So this is the sample mean, and this is a true mean. So I can get the subtraction and see if this is almost 0, then the true mean, the sample mean is equal to true mean. So we need to measure the difference. So here we have the absolute value for the difference of the sample mean and the true mean. And since here is a sample mean, that's the variable. So if I minus some fixed number, it is still a variable. So this term is still a random variable. So we were going to measure the probability of this difference greater than some epsilon. That is the tolerance level. What is this probability? So here's a theory for the weak law of large number. I have x1 to xn, and they are ID. They are ID random variable, and they have the mean mu. So if I have epsilon that's greater than 0, then for the probability, this probability when n goes to infinity, this probability should be 0. That's the weak law of large number. How do we prove this? To prove the weak law of large number, we need two probabilities in inequalities. So we need to know what Markov's inequality is, and also what Chebyshev's inequality is. So first, let's see the Markov inequality. So for the Markov inequality, that this random variable x is greater than 0, this is non-negative. And for any epsilon greater than 0, then we have this probability. Probability of this random variable greater than or equal to this epsilon. This probability will be less than or equal to the expectation of your random variable divided by that epsilon. So let's prove this. First, let's probably just take the epsilon here. So epsilon times the probability. So for epsilon times the probability of x minus greater than or equal to epsilon. What is the result for the epsilon times the probability? That is epsilon times the PDF of x, and this probability is x greater than epsilon, so the integration will be epsilon to infinity. And since x is greater than epsilon, so this is less than the epsilon to infinity. Now I change the epsilon to x. Here we say because x is greater than or equal to epsilon. And now this integration is from epsilon to infinity. I can also change that to, if we compare to minus infinity to infinity, maybe just 0. 0 to infinity, x times f of x. In this case, the right hand side is greater than or equal to the left hand side. here you can also put that to minus infinity. Consider all possible outcomes times the weightings, that is the expectation. So you can see the left hand side is less than or equal to right hand side, and I can divide by epsilon, then we get this one. This is Markov inequality. Next, let's see the Chebyshev inequalities. For the Chebyshev's inequality, I have random variable x with the mean mu. And for any epsilon greater than 0, then we have this expression. Probability of your random variable minus the mean. The absolute of that value should be greater than or equal to the epsilon. This probability should be less than or equal to the variance divided by the epsilon squared. So here's the proof. And for this proof, we can use the Markov inequality. Okay. We apply Markov inequality. To show that the probability of the x minus the mean greater than or equal to epsilon equal to the probability. That means the random variable x minus mean squared should be greater than or equal to epsilon squared. Now this is your x, and epsilon squared you'll be the original epsilon. So from the Markov's inequality, it should be expectation of your x. Now your x is x minus mu squared. Divided by epsilon becomes epsilon squared. So less than or equal to expectation x minus mu squared divided by epsilon squared, which the numerator is variance of x divided by epsilon squared. Okay, so now we have the Markov's inequality and Chebyshev's inequality. We can go back to see our weak law of large number. How do we prove that? So now back to the proof of weak law of large number. Let's go back to see the weak law of large number. Here I have a probability of something greater than epsilon. Okay. So here the probability of your mean, sample mean minus true mean, that's greater than epsilon. From the Chebyshev inequality, so for the Chebyshev inequality is less than or equal to the variance divided by epsilon squared. And what is the mean? the variance of the mean that's equal to the variance of any random variable because they are ID divided by n. Because let's see, what is the sample mean? The sample mean is the sum of the random variable divided by n. When I take the variance, that's the variance of the random variable x1 divided by n. So in this case, for the variance, if I have a coefficient, actually I can put it outside and time n squared. So it should be 1 over n squared variance of x1 plus 1 over n squared times variance of x2. And so on till 1 over n squared, the variance of xn. So that's why it is the variance of, you can choose any one because they are ID. So x1 divided by just n because they are the same. And I have n terms. Then, therefore, this probability is less than the variance divided by n times epsilon squared. And when I take the limit, it should be less than or equal to the limit n goes to infinity. So when n goes to infinity, that's 0. Alright, that is the weak law of large number. The next one is a strong law of large number. For the strong law, let's see the difference. It's like the probability of what? This probability of, I still have the subtraction, the difference of the sample mean and the true mean that let the n goes to infinity. And this difference should be greater than the epsilon. That probability is equal to 0. For the weak law of large number, it's like I put limit outside, and the strong law I put limit inside. Okay, and for this strong law of large number, that proof is beyond the scope of this course, so we just skip. Okay. So next theory is the central limit theory, most powerful and popular theory. what is the central limit theory? I have a simple mean, and simple mean has a distribution. And this distribution will eventually converge to the Gaussian distribution. So when n goes to infinity, this distribution is Gaussian. And why the central limit theory is so powerful? Because it can work for any distribution. So for x1, x2 to xn, whatever distribution your distribution is, then once we have the simple mean, and then when n is big enough, then this simple mean will become Gaussian. X1 could be exponential, x1 to xn could be exponential, could be geometric, could be binomial, but eventually the simple mean of the distribution will become Gaussian as long as n goes to infinity or n is big enough or is large enough. So here's the theory. x1 to xn are ID, random variable, and any distribution with the mean and the variance. And also the third moment is finite. Then for this simple mean, when n goes to infinity, simple mean is Gaussian with the mean mu, and the variance sigma squared divided by n. And we can rewrite that to get the Gaussian with zero mean and variance 1. So in that case, the probability can approximately found for this simple mean. So the probability will be Gaussian at any point minus Gaussian at the starting point. For getting the zero mean and variance 1, we are doing the standardization. So this part is standardization. For example, if I flip the coin 100 times, and x, this random number, is the number of heads, then if I do 10,000 experiments, then this random variable x, the number of heads, so doing that, x is number of heads, so the x is binomial. Okay, with their parameters 100 times and the probability. So this is 100 times. And the expectation is MP. And the variance is NP 1 minus P. So now let's see the mean of the sum of random variables. So the mean or divided by n of my random variables x1 plus x2 till xn. And the expectation of the sample mean is NP, and the variance is P times 1 minus P. But when n is large enough, by the central limit theory, the sample mean will become Gaussian. If I want to find the sample mean, the probability of this sample mean that's between 45 to 55, then we can use this phi function. 55 minus the mean, which is NP, divided by square root of P times 1 minus P, minus, now 45 minus mean, divided by the square root of P times 1 minus P. If now the x is Bernoulli, not the binomial, and I flip the coin 10,000 times, what is the mean? The sample mean, the mean of the sum of the random variables. This mean is we don't know how many, right? So always x1 to xn, and this time it's 10,000 times. Then the mean of mm, or the sample mean, is the mean of, you can pick anyone, because the ID, and suppose it is well, Bernoulli, so it's P, and the variance is the variance of x1 divided by n So by central limit theory, your sample mean will become the Gaussian with the mean and variance. So if you want to find the sample means between 0.4 to 0.6. Here divided by the variance, and then the starting point, and also the starting point 0.4 minus the mean divided by the variance. Now let's continue the last one. X is Laplace random variable, and for Laplace random variable we have the PDF, and also we have the variance. And the x1 to xn are IID, Laplace random variables. So the mean, it should be m 100. Okay, so I have 100 random variables, and I try to find the mean. That's simple mean. I want to find the expectation of x, and let's find the expectation first. And for Laplace transform, the mean should be, you see this is symmetric about y-axis. So the mean should be, if you do the integration, that's 0, because symmetric about the y-axis. And the second one, if lambda equals 0, then use the Chebyshev's inequality to find the lower bound. So if lambda equals 0, 10, we know the mean is 0, and the variance is 2 over 100 squared, 100. So by Chebyshev, inequality, the probability of the m 100 minus 0, that's greater than 0.1, should be less than or equal to the variance divided by n 0.1 squared. And we can also find the upper bound. There will be 1 minus probability. Using the probability properties, and this is also the axiom. So let me see. This is greater than 0.1. And then we can also use the central limit theory to find the probability. So for the central limit theory, with 0.1 minus the mean 0 divided by square root of 2 divided by 100 divided by square root of 100. So you just check the table later, okay, the Gaussian table. All right, that's just for the limit theory. Okay. Next, we are going to talk about the random process. So random process is just an extension of the idea of a random variable. Okay. So in the past, the random variable, we map the outcome or realization to the number. Now we map the same thing but to the function of time. So that means in the past we have a sample space here. This is our sample space. And we have the realization or the outcome C1, maybe C2, and C3. We'll map to a function of time, which means see if I can copy and paste. Okay. So for C1, I map to x of the function of time t and C1. And suppose it is a sine wave. And for C2, I map to the function of time for C2. And it could be a square wave chain. And for C3, also I map to function of time. So it could be a triangle wave. So I observe the temperature hourly in, for example, New York Taipei or Tokyo in 3 different cities. Or in the same country, I measure the temperature hourly in Taipei, Tainan, and Kaohsiung. Okay, like at noon. So suppose at noon, and here I will get the temperature in Taipei, Tainan, Kaohsiung. And in different time, like in the morning, I also have a different temperature. So if we pick a particular point, like at 12 o'clock, so suppose here, this one, okay? This is T naught. Then my X here is X T naught plus C1. And in Taichung, maybe this is the temperature. And also in Kaohsiung. So if I fix the time, actually this T naught kasi is just a random variable. And later on you can see that through this random process, I have the temperatures in Taipei, Tainan, or Kaohsiung, or different cities. And with those data, we may also analyze something. So a random process for the first definition. The random process is a collection of random variables indexed by t. And this t could be discrete or continuous, like every hour or in the next 24 hours. And if t is uncountable subset of the real line, then this random process is called the continuous time random process. And if t is discrete, then we say that the x of t is the discrete time random process. We will write that x of t to say it is a random process. But typically, we should have a notation like t and c, or just have like 2 symbols here. To use x of t is just like if we just denote x, that is for the random variable. So x of t, that will be the random process. We use x to denote a random variable. So if we have this notation xt c, it is a random process. If I fix the t, then it is a random variable. Then this is a random variable for a fixed t naught in t. Then how about that if I fixed this cassette? So it's cassette not. So if we fix cassette, you can see what does that mean. If I fix cassette, that this one I fixed, it is all cassette 1. So it is a function of time. This is also a function of time. A function of time. So it's called a sample function. Is a sample function or we say a function of time. Okay, let's see an example. A is a uniform random variable from 0 to 1. And then x of this random process is a of cassette times cosine 2 pi t. That means you can also write it down. This is x of t equals a is a random variable, cosine 2 pi t. So if I fixed t, say t equals 10, that means x of 10 cassette, that'll be a of cassette cosine 20 pi. And you can see this cosine 20 pi is just a constant, so it is a random variable. We only have a, that's random variable. If I fix cassette, say a of cassette is 0.8, then you will see this random process 0.8 t a. No, it should be put time first. T 0.8. This is just 0.8 cosine 2 pi t. And you see this is a deterministic function in t. And this is the example for continuous case. Next, let's see the discrete case. Random variable a is a discrete, and we have the PDF for this random variable a. And now we have a random process. This is the expression a over c times -1 to the n. If I fix n, say n equals 8, then x of n c is equal to x of 8 c. It'll be either -1 to the 8th or -1 to the 9th. So with a probability of 1/2, it could be either 1 or -1. And you can see that this is just a random variable. since A is either 1 or minus 1. If I fix C, then x of n C is going to be either minus 1 to the n or minus 1 to the n plus 1. When A is 1, there will be minus 1 to the n. And if A is minus 1, then it will be minus 1 to the m plus 1. So you can see this is the time series. Now next, let's take a look about the probabilistic description of a random process. When we learn the random variable, we will learn their PDF, CDF, and also the expectation variance. Or do we have the PDF or CDF for the random process? And yes. So we can use the CDF or PDF to describe the behavior of the random process. So, and the random process evaluated at a particular point in time. So if I just like this is that fixed time, this random process is a random variable. So now, what is the first order CDF of random process, and also first order PDF of a random process? CDF is probability always. So here you can see that the CDF is the probability. The probability of your random process less than or equal to some point, that is your CDF, and it is called the first order. And here's the notation. Then for PDF, we just take the derivatives of our CDF, and this is your PDF. And for the CDF, you can see that this function is a function of x and t. And normally, we are interested in the different time of your random process, and we will see some examples, okay, later. So they may try to find the difference, like, okay, the temperature at 10 o'clock in the morning, and at noon, or in the afternoon, in the evening, or at midnight. So with a different time, what's the relationship between those data? We can also define the CDF. Here you see that this is a first order. You may be curious that what does that mean, first order? Then do we have a second, third, or more? And yes, here for the nth order, what is the nth order CDF? For CDF, we know it's a probability. So there will be the probability of the first fixed at x1 at t1 less than some point, at t2 less than some point, and tn less some point. And so we do the intersection of this in different times, and I want to find the CDF. Then this is a probability of that intersection of each random process at the specific time And then the nth order PDF, we just take the partial derivative with respect to x1 to xn. And then we know the PDF and CDF. How about the expectation? Here we have a mean function. For the mean function, we just take the derivative, take the expectation of the random process. For example, if my random variable a is uniformly distributed from 0 to 1, and then my random process is a times cosine 2 pi t. What is the mean function of x? So first, the mean function of x at 0, that means expectation of x at 0. So t is fixed. This is the random variable. So it will be expectation of a is random variable, cosine 0 is 1. So expectation of a is uniformly distributed, so the expectation is 1 over 2. So overall, if I don't specify the time, so the mean function is expectation of x of t, and it will be a cosine 2 pi t. And you can still see that the 2 pi t is nothing related to the random variable, so I can put it outside. Times the expectation of a, that will give you 1/2 cosine 2 pi t. Right, let's see another example. Now that the theta is the random variable, also uniformly distributed, and we have a random process cosine omega t plus theta. Every time you need to make sure that which one is random variable. Okay, now here theta is the random variable. So if I want to find the mean function, will be cosine omega t plus theta. So consider all possible outcomes. Here we see that this is a random variable. Okay, so this is the function of random variable. So consider all possible outcomes and possible function of outcomes times the weighting. This weighting is the PDF of your theta. So it is uniformly distributed. So from minus pi to pi cosine omega t plus theta d theta. Also 1 over 2 pi d theta. And you get 0. Those are the two examples for continuous case. Let's see a discrete case. X random process is a to the n. So a is uniform. A still continuous. A is uniform. Well, but n is discrete, so x and the mean function will be expectation of x n will be expectation of a to the n. So a is continuous. So consider all possible outcomes dA. So there'll be 1 over n plus 1. Next is the variance function. So here's the definition of the variance function. So for the variance function of a random process, here, still the mean, and then random process minus the mean function overall square. So both the mean function and the variance function are function of time, function of t. And then autocorrelation function of a random process. For the random process, you can see that we have a function of time, right? And this is x. At the t1, this is t. At t1 and t naught, so I may have those two values. What's the relationship between these two values? We have the autocorrelation function. So for the time t1 and t naught, there'll be the expectation of x at t1 times x at t2. So this autocorrelation function measures the correlation of two random variables, xt1 and xt2. So these two random variables at t1 and here at t2. Next is the autocovariance. So autocovariance, also the random process minus mean times the random process minus mean 1. Here's a note. You can see the relationship between the autocovariance and the autocorrelation. Find out this one. So the relationship between the covariance, autocovariance, and also autocorrelation. Autocovariance, there'll be the autocorrelation minus the multiplication of their mean functions. If the time is the same, we fix it at the same time, then autocovariance becomes the variance. Let's see why this equation holds. First, what is the autocovariance? T1, T2. Okay, from the definition here, by the definition, and then you can take the square, take the parentheses out. So you redo the multiplication. We have x t1, x t2 minus x t1 mean function for t2. And x t2 times the mean function at t1. Then plus the multiplication of their mean functions. So it will be from the linearity of the expectation. I have expectation of t1 and the random process at t2. Second term, x of t1, and then mean function at t2. And then next term, expectation at t2 and the mean function t1. last term. Okay, so the first term is autocorrelation. The second one, we'll take the expectation. This is the mean function. Okay, so we can put it outside. And you fix the time, so it is a random variable. And this actually also is the main function at T1. And the third term, similarly, we put the main function outside, take the expectation, and this is mean T2. And then last term, there'll be no expectation. So we'll cancel out. Therefore, it is the autocorrelation minus the multiplication of U. The multiplication of the main functions. Now here's a note. The cross-correlation function of x, random process x and random process y, we can write it down auto cross-correlation. R over xy, T1, T2. That is the expectation of x, T1, y, T2. And the cross covariance. So for cross covariance, let me see x, y, T1, T2. That is the expectation of your random process minus your mean function. But order matters, so here I have a T1. So mu x T1. And then the second one will be T2. So y at T2 minus mu y at T2. So if the mean function is 0, then the cross covariance T1, T2. Since mean is 0, there'll be the multiplication of your random process and take the expectation. So the autocovariance is equal to the autocorrelation. Only when the mean functions are 0. So let's take an example. You will see how it goes. A is uniformly distributed, and x, the random process is a times cosine 2 pi t. So let's find the mean first. So the mean function is expectation of your random variable a and cosine 2 pi t. So this gives you 1/2 of your cosine. Then the autocorrelation T1, T2. So I have expectation of a cosine 2 pi T1 and a cosine 2 pi T2. Okay, so T1, T2, this cosine, we can put everything outside. Cosine 2 pi T1 and also times cosine 2 pi T2. I only have expectation of a times a, so expectation of a squared. That's 1/3 cosine 2 pi T1 times cosine 2 pi T2. And the autocovariance. Since the, let's see, the mean. Well, the mean is not 0, so that's fine. Is equal to the autocorrelation T1, T2 minus the mean function so you will get 1/12 cosine 2 pi T1 and the cosine 2 pi T2. Next example, theta is uniformly distributed from minus pi to pi. And let's just find the autocorrelation. So for the autocorrelation, that's the expectation of your, you see that the order, x here you should put T1 and then x T2. So it's cosine omega T1 plus theta and cosine omega T2 plus theta. And this is 1/2 cosine omega T1 T1 plus T2 plus 2 theta plus 1/2 cosine omega T1 minus T2. Okay, so here for cosine A times cosine B, if I have a cosine A times cosine B, that should be 1/2 of cosine A plus B plus 1/2 of cosine A minus B. And you can see that this is nothing related to theta, so I can put this is just like a constant, put it outside. So 1/2 expectation cosine omega is T1 plus T2 plus plus 1/2 this constant. And this expectation is 0 because cosine is an even function. So overall, it is a time function. 1/2 cosine omega t1 minus t2. Okay, next, let's talk about the independence. For the random variables, we know that if they are independent, what does that mean? The joint PDF will be the multiplication of their marginal PDF. Same thing to CDF, and also expectation or even characteristic function. For the random process, if two random processes are independent, that means their CDF can also be separated and times together. So for the CDF, the joint CDF, x t1 to x t n and y t1 to y tn. So here's x1 to xn, y1 to yn. This becomes the multiplication of their individual CDF fx t1 to x tn. Do I have? Yeah, we have a capital. Good. x1 to xn times the CDF y t1 to tn and to yn. For uncorrelated, we said two random processes are uncorrelated if their expectation here x times y is equal to this multiplication of their main function. If x and y are equal, it becomes the autocorrelation, or x t1 t2 will be equal to expectation of x t1 x t2, and this is the main function. Again, if they are independent, that means they are uncorrelated. But the other way around, it is not always true. All right, so far we just talked about the random process, and actually random process is pretty difficult. And to study all the random process, it could be also a semester course. So we just now for the rest couple hours, we just focus on a subset of random process. It's called strictly stationary process and Y-sense stationary process, especially for the Y-sense stationary process. Okay, so first, what is a strictly stationary process? A random process is called strictly stationary if their probability description, like CDF or PDF, is invariant to shifts in the time origin. So if I shift in time, their probabilistic description won't change. Then it is called a strictly stationary. So you see that my CDF, if I switch to a right with a tau, their CDF is the same. So for the first order CDF, the CDF must be independent of time. So if I shift by tau, the CDF is the same. That means my mean function is also the same. There'll be a constant. And also the variance is sigma squared for OT. For the second order CDF, it depends on the time difference. Only depends on time difference. You see, if I have a T1, T2, actually we can think of 0 and the time difference. So the autocorrelation T1, T2, it also depends on the time difference, T2 minus T1. And then autocovariance, same thing. So it doesn't matter that if I have a timeline here, I have a T1 prom, T2, and T2 prom. So this is the tau. Okay, tau 1, 2 is the time difference between T1 and T2. And here is tau 1, 2. It only depends on the time difference. But for the strictly stationary, I probably need to check a lot of CDF, first order, second order, or even high order. So it is also it's hard to check the entire CDF. And then it is also not feasible because the CDF may be complicated. Therefore, we just focus on the Y-sense stationary process. So what is the Y-sense stationary? It is a random process is called Y-sense stationary. If first the mean function is constant, and then the autocorrelation depends on time only. Therefore, if this random process is strictly stationary, it is also vice and stationary. But the vice, not versa, here it cannot apply. Vice and stationary doesn't mean it is strictly stationary. And for the vice and stationary, how about the autocovariance? For the autocovariance, here we can say this is the autocorrelation T1, T2, and then the mean function. And since X is random process, so here the autocorrelation depends on the time only. So T1 minus T2. And the mean is the same. So therefore, this autocovariance is also, autocovariance depends also only on the time difference. And why do we study the autocorrelation and vice and stationary? If the random process is vice and stationary, then everything is characterized by the autocorrelation. And since the mean function is a constant, so we don't really worry about the mean function. And the autocorrelation will tell you how much correlation you have with a sample, with a distance tau away from you. If the autocorrelation is small, then you may say that you and the sample has the weak correlation. And if the autocorrelation is a delta function, that means you only correlated with yourself and no one else, like white noise. And since looks like vice and stationary is important, and a lot of things that we may use the vice and stationary and also the autocorrelation. Let's see the properties of this autocorrelation. First, if the time difference is 0, that is the average power of the random process. Because the autocorrelation with 0, the time difference is 0, you can think about the expectation of x t plus 0, and the other one is t. So the time difference is 0, and that is expectation of x squared of t. And this is the average power. And the autocorrelation is symmetric, since we know this is the time difference, so t plus tau and x of t. But I can also rewrite it is just the time difference, so x of t n times x of t plus tau. If we switch the order, we also have the first minus the second. The first minus the second will be minus tau. So r of x at minus tau. The third, the autocorrelation, the maximum value is at origin. We can use the Cauchy inequality. So by Cauchy inequality expectation of xy overall square will be less than the expectation of x squared times expectation of the second moment y. So for the autocorrelation squared, let's compare it. This is x squared and this is, well, this is x and this is y. Will be less than or equal to these two will be, here you can see this is equal to, because they are the same. Okay, so this is the expectation of x squared t overall squared, and that's the autocorrelations at 0 squared. Let's see an example. We have a random process a times cosine omega naught t plus theta, and two random variables a and theta. They are independent. Theta is uniformly distributed from 0 to 2 pi. A has the mean mu a and the variance. I want to know if this random process y-sense stationary. To check the y-sense stationary, first I need to see the mean function. The mean function should be the constant, and the autocorrelation should depend on the time only. So these two properties. First, I want to check the mean. So the mean function a cosine omega naught t plus theta. Since a and the theta are independent, so I can separate that. Expectation of a and expectation of cosine omega naught t plus theta. The first one is mean a. Second one, consider all because it is uniformly distributed from 0 to 2 pi, function of outcomes, times the weighting 1 over 2 pi, and this becomes 0. So overall, it is 0. And 0 is a constant. So at least the first step, we check the mean function, it is a constant. Second, we would like to check the autocorrelation. For the autocorrelation, T1, T2, x T1, x T2, so it will be a cosine omega 1 T1, omega naught T1 plus theta, and the second one a cosine omega naught T2 plus theta. Again, random variables a and theta are independent, so I can put O A outside, and then the other expectation is cosine omega naught T1 plus theta times cosine omega naught T2 plus theta. So how do I get A squared? Do I need to really do the integration? No, we have the mean and the variance. So since we have the mean and variance, we can definitely know the second moment of A. That should be mu A squared plus sigma A squared. And then we just found the expectation for the second term. That's 1/2 cosine omega naught T1 minus T2. The mean function is 0, which is constant. And also the autocorrelation is a time difference. Therefore, x is y-sense stationary. Let's talk about the power spectral density. So the autocorrelation is a function of a time difference. So if it is only the time difference, we can also analyze this function in frequency domain. So here is a definition for the power spectrum, or we call power spectral density. So the power spectrum, or we call power spectral density of a y-sense stationary random process, it is actually the Fourier transform of its autocorrelation function. So here's a definition. If we take the Fourier transform of our autocorrelation function, it is the power spectrum. So later on, you can check the table, the Fourier table. For example, autocorrelation function in this way, then the spectrum will be four alpha divided by 4 alpha squared plus omega squared. Just check the table. You don't really need to calculate the integration. So suppose here is an example. Random process is A cosine omega naught t plus theta. Theta is random variable. And apparently A here, A is not a random variable. So the autocorrelation, we can find the autocorrelation to be A squared over 2 cosine omega naught tau. So it'll be A squared omega cosine. We can also express the cosine using the Euler formula. So it will be exponential I omega naught tau plus exponential minus I omega naught tau divided by 2. And we can take the Fourier transform. The Fourier transform of both sides. Then the left-hand side is the power spectrum. And the right-hand side, we can check the table, the Fourier table. So we have delta function, omega minus omega naught, is doing like a time shift, or not time shift, doing the shift, like modulation. So now let's see the properties of the power spectrum. We have four important properties. First, the power spectrum. Instead of doing the integration from minus infinity to infinity, we can just consider the right hand side and then take to double it, because the autocorrelation is symmetric. So since autocorrelation is symmetric, then we have put here. We can put 2 So when we have the minus infinity to 0, that's this part. And then since it's called power spectrum, so the power spectrum is non-negative. So must be non-negative. And then if we take the Fourier transform of the autocorrelation, we get the spectrum, which means I can take the inverse Fourier transform of the power spectrum and I will get the autocorrelation. And how about the second moment of the random process? For the second moment, we can prove that that means the time difference is 0. So we have where? Yeah. So we have this form, the integration. Let's see this example for today's last one. The band limited white noise. So the white noise here's omega. And I give you the spectrum. Is minus W, not omega. Okay, W. Here is n naught over 2, 0. We try to find the autocorrelation. If I have a white noise with a spectrum, here we need to see the Fourier transform pair. If I have a rectangular pulse, omega divided by 2W, it is either 1 or 0. Okay, when the omega is between minus W and W. Otherwise, it's 0. And this Fourier transform is W divided by pi sinc function W tau. So now the power spectrum is n naught over 2 times the rectangular pulse omega divided by w. So here the Fourier transform will get the autocorrelation. That's n naught over 2 w over pi sinc w tau. And when tau is 0, it is n naught over 2 times w over pi. Here we can plot, we can plot here. So you can see that when w goes to infinity, what happens? If w goes to infinity, for the spectrum, it's a flat so it's a line. Here's n naught over 2. And then the autocorrelation. And then when w goes to infinity, it will become a delta function. Okay, because you can see that the w goes to infinity, they will just shrink to the origin.